Hello, everyone. Welcome back to our class. Today, we're going to cover the single and double precision conversion. So this example we're going to convert negative 2.45 to binary floating point single and double precision. For the purpose of this example, I'm going to just do single and just point out the difference it would have been if it was double. So let's start. So this question is negative 2.45 to binary floating point single precision. I always tell my students that before we go through this, I want you to drop the signs and just deal with it as it is. Then we figure out the signs and we'll be able to go ahead with it, right? So 2.45, negative 2.45, if we drop the negative, is going to be 2.45. It is literally 2 plus 0.45. And to convert this one, the first thing you need to do is that you convert this one to binary. To convert 2 to binary, the answer is 10. So 2, the answer is 10. To convert 0.45, that is where people struggle a little bit. So I'm going to show you how it's done. You're going to take the 0.45, you multiply it by 2. The answer you're going to get is 0.9. So as soon as you get this part, 0, is going to be part of the answers that we're going to use. And we're going to take everything after the point and multiply it by 2, which is going to be 0.9 times 2. And I believe the answer is going to be 1.8. Yes, it is. I'm going to do that here. 1.8. Now, because there's a 1 before the 0.8, we're going to keep it. It's going to be part of our binary conversion. Now, we're going to take the 0.8 part. We're not going to use the highlighted one part, only the 0.8 part, and we're going to multiply it by 2. So you see, the algorithm, it requires us to keep on multiplying it by 2 until we get 0. So now I'm going to do the same thing. So the 0.8 part times 2 is 1.6, which means we get to keep the 1 from here. Move it over here. Cool. Now we're going to repeat this for a while. Let me things that I already did. So to prevent wasting much time, I have this written out, which is when we got here, we picked only the 0.6, which is this line, and multiplied by 2, we got 1.2. Means we get to keep this 1. Now, we got here, 0.2 times 2 is 0.4. So the one before the point is 0, so we get to keep 0 here. As you see, it's going to keep going. So we're going to keep 0, we're going to keep 1, we're going to keep 1, we're going to keep 0. Some of you may not have realized this, but I have a pattern that I have received, I have observed. I'm trying to highlight these to yellow so that we know where we got this part of the numbers from. Usually you would continue this until you get 0.0 and you can continue the multiplication. But as you can see, after this line, from this line to here, we started seeing a repetition. So the part I've highlighted, this one, it got repeated here. Let me highlight this as green and realize that it got repeated down here. So it's going to continue repeating until we want to stop. So this part repeats this. So we know that we can stop and write it in the form. So this, let me delete this part. So 2.45 is going to be, the 2 part is 10. And point, if you like, 0. No, 0 0.011100110. Here, we got it from here, 0.111001110. In fact, we could continue writing because it's repeating. So we can continue writing it. But, mathematical notation is that we just identify the part that repeats and put a bar on top of it. I'm just going to highlight the part that repeats here. This is the part that repeats, and you can see it here. So we can just end after the blue line. Good. So now we know how I got this number. I'm not going to need this table again. So I'm going to put it away. And I'm just going to continue typing for this one. All right. So after we get this, the next thing we're going to have to do is normalize it. Normalizing means that in this binary, we want only one at the left side of the point. So we want 1 point something times 2 raised to the power something. So we're going to move this point from here to here. It's going to give us, so I'm going to copy this line, copy it, bring it down here. I'm going to move the point to this place instead and delete this one. As soon as I move the point, I'm going to have to do times 2 raised to the power 1 because we only moved it once. Let's see, then we times 2 raised to the power 1. We moved it once. So at this point, the thing you should know is that this one here, after we normalize it, this one here is what we call unbiased exponent. Unbiased exponent is not the exponent we need for this conversion, but it's a very good exponent that we need. So basically, your biased exponent, which is the one that we require in this conversion, in this table, the biased exponent is supposed to be your unbiased exponent plus a bias. What bias do we need to use? If it's a single precision, the bias is 127. If we're doing a double precision, the bias is 1023. As I said when I started, I'm only going to work with a single precision for this one. And then I'll tell you the difference that it would have been if it was double precision. So let's just work with a single precision. So now our biased exponent is going to be 1, which is from this place, plus the bias for a single precision is 127, which will give us 128, right? So we have a bias exponent of 128, and we know that the number that we were converting was negative. The first one is the first bit, as you can see, is a sign bit. So if the number is negative, you put 1 as the first bit. If the number is positive, you put 0 as the first bit, as the first bit. So I'm going to try to see how I can insert a table with 3 parts and do this one. Okay, so I have this table which is similar to this one. So let me move this line here. This is going to be a little one. Let me move this one here. So from the algorithm, we're going to put 1 here because 1 is the bit sign, and this question says negative 2.5. Since it's negative, the first bit is going to be 1. If it was positive, the first bit was going to be 0. Now this part is from this table, it says is an 8-bit bias exponent. We've already found our bias exponent to be 128. And the binary for 128 is 1 0 0 0 0 0 0. So now we are almost done with conversion to single precision. The only part that is left is the 23-bit fraction of the mantissa. The mantissa or the fraction is gotten from when you go to the normalized form. Anything after the point is going to be your mantissa or fraction. So I'm going to copy and paste that one here. So usually when you get this and you don't have anything, so you get a 23 bits. But remember, this one we can't because it's a repeating number. So we're going to have to pad this with the numbers until we get 23 bits. I don't know how many bits we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I keep on adding 4, it's going to be 15, 19, and 23. So this is our conversion to single precision. This converting binary floating point to single precision. If we were converting it to double precision, what would have happened is that the binary here, the bias exponent here would not be 128. would have been 1023. No, no, sorry. The exponent here will not be 127, would have been 1023, which means that our biased exponent would have been 1024. And we represent that in 11 bits instead of 8 bits. So that would be the difference if we were doing single precision. I mean double precision. I hope you understand. So yeah, this is what I wanted to show you. The first one, as soon as I see the one, I know that the number is a negative number. This is my biased exponent. If I want an unbiased exponent and I know it's a single precision, I will just subtract 128 from this, which in this case will give me 1. And this is my mantissa, which is everything after the point. I think this is all for now. Have a good day. Bye.